Okay, we're going to be working some of the homework problems, and I would like to put up the homework problems. And I can do that by sharing my screen and sharing my appropriate screen. I think this is it, right? Prove both De Morgan's laws for fuzzy min-max logic, prove the Jaeger and Seguino complements are involutive. That isn't obvious by looking at the equations. I think that was really cool. Offer an operation for a fuzzy exclusive OR. So I'm going to call, okay, we still don't have Trevor here. Okay, Sam, you're number 0. Colin, you're number 1. Minkun, you're number 2. Matthew is number 3, and Innocent is number 4. Now, because we have 4, how many coins will I need? In binary. Each of the coins comes out binary. How many do I need?
2.
2, I can get 0, 1, 2, 3. No, see, I can't get 4. I'm going to need 3, right? You agree with me?
Oh.
Some
yeah,
of
I forgot you were counting 0.
Yeah, that's right. That's right. Well, 0 is tails. So that's the reason we start at 0, just like, is that C++ where you start at 0? Okay, we have a Susan B. Anthony and 2 nickels. So it's Sam, you're the lucky one. Do you want to try the first one then, which is to prove the De Morgan's laws and just kind of go over them, at a higher level. And then we'll drill down if there's anybody that has any questions. And I believe what I need to do is to stop sharing, and I need to give you permission to share your screen.
Great.
Nope, that's the wrong one. Wrong one. Security, share screen. Okay, there's Trevor. We missed you, Trevor. What's Trevor? 0, 1, 2, 3, 4, 5. Trevor, you're 5.
Okay, so apologies in advance. My scanner is doing weird stuff. I'll have that fixed for next time. So here, the first De Morgan's law is this. So I started with a few axioms here. And I'm happy to talk more about those if there are any doubts about them. So axiom 1 is that it says this, that if you switch around the arguments,
that's interesting.
The other one will be, if you switch around the sign of the arguments, then the min becomes the max, and then you get the negative answer out of it. So you got to switch the sign again to get your original out. So I took this as an axiom, and I just used inequality logic with multiplying by -1 there as my inspiration for that. And then axioms 2 and 3 are pretty much the same. If you add a number to the maximum of 2 numbers, it's the same as adding that number to to both of the arguments. So like if you had 1 and 2 plus 1, that'd be the same as 2 and 3, because you'd get 2 plus 1 and you get 3.
Sure.
So I took these for granted here. And so with assuming those 3 things, the proofs are relatively short. For the first De Morgan's law, I started with the right side. I used axiom 1 to switch all the signs. And then I pulled out the -1, and then the negative distributes. And then
okay, that's great. And it's basically the same for the next one then, right?
Right. Yeah, it's very analogous.
Well, Sam, I think a mathematician would be very proud of you right here. Because this is the way a mathematician would do it. They like to start with axioms and stuff. This is very formal. Okay, any questions on that? Or anybody want to offer a new, insightful, different way of doing it? Or is this about it? Okay, if not, let's go on to the next question. And I got to make a little note in my book here, because you get graded on class participation a little bit. Okay. Wow. Innocent, you're there with your twin brother. You're logged on 2 times. That's cool. I'm sure you have a good reason. Do you have a good reason, Innocent, for being on twice?
Yeah, I logged in with my phone the first time, so I'm trying to log out and use my PC now. Yeah.
Okay, you can use them both. That's fine. I don't care. Okay, let's see. Now we have heads, tails, heads. That's a 5. And that who's number 5? Trevor. Okay, you're on, my friend. Do you remember what the problem is? Put your screen up and tell me what the problem is. Or wait, did we finish with the one? We did the De Morgan's Law. Okay, yeah, we're done with one. Okay, what's the second one, Trevor?
So the second one is showing the Sugino and Jaeger complements, and if they're involutive. So can you guys see my screen?
Yes.
Okay. So so for this first one, we have the Jaeger, which U of A is equal to 1 minus A to the W, all in parentheses of 1 over W. And so if you were to plug that back into itself, the A then becomes this entire U of A. So then you have this long, complicated multiple exponentials, A to the W to 1 over W to the W to the 1 over W.
Okay, never read an equation.
Okay.
Just point to it and say, boom, there it is. Okay. And maybe explain it at a very high level.
Okay. But then these exponents can cancel out, and as you start applying them, all of the math kind of works out, and so you're just left with A.
Okay, and the Sugino is kind of the same, isn't it? Yep.
Yes. Takes a little more work because it involves multiple fractions, but you can just multiply by the denominator, which is the 1 plus lambda A. Those will cancel out, and you're left with a nice little A times 1 plus lambda over 1 plus lambda, which just leaves you with A.
Okay, so one of the things about this is, I don't know about you, but I look at those equations, it isn't clear to me that it is involutive. But you turn the math crank and boom, it pops out, right?
Mm-hmm.
So very interesting. Okay, thank you, Trevor. That's good. Okay, so we are sampling, by the way, without replacement. So somebody else will get this. So you're narrowing down. Okay, heads, tails, tails. What's that? 4? Who's 4? Who is 4? Ming Kun, is that you?
Number 2.
You're number 2. Okay, we're number 2. Okay, great. Matthew, I don't know, you number 4?
I thought I was 3, but I can go anyway.
Okay, well, okay, go ahead. Go ahead. This is fine. We're not doing this scientifically, and I have developed a short-term memory the length of a goldfish. So I can't remember those things. In fact, I can't even remember if I've told you before that my memory is that of a goldfish. Do you know why it's a goldfish? The goldfish has a short-term memory of 3 seconds. So after that, it loses everything. And I think maybe the people that are happiest in life maybe have a memory of a goldfish because you forget everything. So, oh, this is great. You did this in Word, it sounds like.
Yep. Learning all the little backslash lambda and all that stuff. It's very handy.
Okay.
I need to use LaTeX, but that's
Oh,
for later.
you did. Okay. So you did use, oh, this is a PDF file, huh?
Yeah.
Okay. And you did it in Word, is that right? So you
Mhm.
used the Word equation editor.
Yeah.
Which is pretty good. Okay, let's see what you got.
So it's pretty simple. Obviously, I need to offer fuzzy XOR. Starting from the crisp logic XOR, which is just A XOR B is, this is one of the definitions. It just happens to be the one I picked. And A union B intersected with the complement of A union B. And then just straight up converting that with mins and maxes, you have the minimum of max AB and the complement of the min. And I didn't immediately see a way to simplify this down, so I left this as is.
Okay, you just called that a C for complement, is that right?
It would be 1 minus using the static complement. But
Okay. Okay, go ahead. Okay, so I think that that's good. Here's a question. Did anybody plot this in 2D to kind of see what it looked like? What should it look like? It seems to me that in 2 dimensions, you have your corners at 1, 0 and 0, 1. They're both at 1, right? And your other corners 0, 0 and 1, 1 are going to be at 0, correct? So I imagine it as if, well, let me draw it. Okay, thank you. Thank you, Matthew. Go ahead and not share your screen then. And I'll try to do this with my camera here. I've switched my camera around, so hopefully we'll be able. So hopefully I'll be able to do this more coherently without balancing my arm, although I think I couldn't. Okay, I am going to pin myself just early so you can see the entire thing. And so here's what we have for the exclusive OR. We're going to have an A and a B here. And this would be the fuzzy logic. This would be the XOR of A and B, which is exactly what Matthew showed. Now at the origin, if we do a little block here, at the origin, the value has to be what? 0. At this edge, it has to be equal to 1. No, it's 0. This is 0 here. This is 1 over here, and this is 1 over here. So I imagine this thing, I imagine that if we were to plot the exclusive OR, it would probably look, it could look something like this. And it would be kind of a valley in here. Or on the other hand, it could be a hump. It could be a hump in there, which was 0 here and here and 1 here and here. But that would be to me a picture of what the XOR would look like. I'm looking at it on my screen and it doesn't look very nice, but it almost looks like a trough. And by the way, what is it along the line A is equal to B in your derivation, Matthew? In other words, when A is equal to B, look at your formula and tell me what it is for A is equal to B. I'll put my camera up.
0.
Put your formula up. Okay, when A is equal to B, the first term is going to be A. The second one is going to be, A intersected with A is going to be A. So it's A complement. So it's going to be A intersected with A complement, right? Or the minimum of A and 1 minus A. So whatever that is going to be along that 45-degree line that we see there. It would be nice to see these plots, and I would encourage you to plot these things to give you a better idea of what is going on here. Now, did anybody else do this differently? I think Sam, you had a different approach that you were talking about. Did that pan out for you?
Yes.
Okay, can we look?
It.
Yeah, if you would.
Sure. Okay, so I just took the maximum minus the minimum, and here I just kind of showed the boundary conditions that does pan out. So for 1, 1, max minus the min, they're equal, so you're 0. You can look through here. And I do have a quick graph of the max minus the min. This is what it kind of looks like here.
Oh, it's great. Okay.
And then I'm almost done doing the method that Matthew showed graphically. I'll be just a second on that.
Okay. While you're talking, I want you to notice, I believe that along the 45 degrees,
It's 0. Yeah.
it's 0. It's 0, which to me is more intuitive. If you take the XOR of something with itself, you kind of should get 0, even if it isn't 1. So I like that property, but again, with these choosing of these fuzzy properties, there is no right solution. So it works out whatever the way that it works out.
Dr. Marks,
Yes.
I plotted the max for the XOR that I had in MATLAB.
Okay. Okay. Why don't you show yours first, Matthew, and then we'll do. Well, that's kind of boring. Oh, okay. I don't see the 3D contours though. I'd love to see the 3D contours. I don't know if you can do. Did you do this in MATLAB or what? You're muted, Matthew.
Yeah. Yeah,
But
this was.
Try instead something like the mesh operation or mesh C operation. I think that that'll give us a better 3D perspective.
If that's being difficult, I did finish my plot if you wanted to look at it. But if you got it, Matthew, that's fine.
Okay, it looks like Matthew.
Yeah,
Okay.
looking at trying to share screen.
Okay. There's certain people, mathematicians, engineers, scientists that are very, very visually oriented. And I'm that way. I like to see pictures. I like to see graphs. Equations are nice. You can give them personality after a while, but seeing a nice graph is a very nice thing to do. Not comparing myself, but Albert Einstein was very visually oriented. He didn't start talking until the age of 3 or 4 or something like that. Is because he wasn't tuned into audible give and take.
I'm not sure what is working, so you can go.
Okay,
ahead.
Sam, go ahead and show yours.
Okay. Kind of looks like this.
Oh, now that is, what did you use? Did you use a mesh operation?
Yeah, just mesh.
Okay.
You have to make a mesh grid of X and Y to get the 2D.
Okay, now I don't see, is it 0 along the diagonal?
No, it bumps up
does.
to a half.
Oh, it does. Okay.
Yeah. Oh, there's the A equals B line is this this line right here.
I see. So that's still a bump in the road, but it does meet the boundary conditions.
Yeah.
Because you can see here the symmetry, which means it's commutative, right? And that's all well and good. So this is as good as an XOR as any of the other things. So we're pretty good. Okay, any luck, Matthew? Maybe we should just wait. Maybe you can show it to us next time. So let's continue. I think that's it, isn't it? That's 3. Yep. Trevor Matthew. Okay. Okay, that's great. We were talking last time about the aggregation operation, and the aggregation operation, if you remember, is aggregation operation, which is parameterized by a alpha. And there's a number of terms in the vector. And remember our idea, we wanted to have this as a representation for a list of numbers between 0 and 1. So all of the A's, for example, are going to be between 0 and 1. And this was equal to A1 to the alpha plus A2 to the alpha plus all the way up to A sub n to the alpha divided by n. By the way, what does this remind you of in probability? Doesn't it remind you of like the alpha moment of a probability density function or something like that? At least the statistical alpha moment. But then we take all of this and we raise it to the 1 over alpha power. Now, the claim is that some very interesting things happen here, such as for, okay, where's my little light? My camera is not having its light on for some reason, therefore I'm getting shadows. Okay, I guess we're just going to have to live with the shadows. I moved it from one side to the other side, so it's a little bit more difficult. So here's the first one, h of minus infinity of a sub 1. And by the way, I could just do a, it's a vector, right? It's a vector of numbers between 0 and 1. This turns out to be equal to the minimum of a sub 1. In other words, you go through this list of numbers and you get the minimum. What the heck is going on here? That doesn't look like that, does it? Now, if you look at the original formula, you get, what is a1 to the minus infinity? Zero, right? So we're getting 0 plus 0 plus 0 plus 0, and all of that's raised to the infinite power, right? So we have kind of a problem. We could solve this using a L'Hopital sort of rule, but another way to do it from an engineering point of view is just to put in some exaggerated numbers. Say, for example, h of minus infinity of a. Well, no, let's not do that. Let's choose a is equal to, and let's take some very interesting one, 10 to the minus 10th and 10 to the 8th and 10 to the 8th, okay? That's going to be our a, and I'm going to put a little t here since I'm a big freak on making all vectors go up and down. So if we do this, what is a1, say alpha is not equal to minus infinity, but it's equal to minus 1,000, okay? So what is this number raised to the minus 1,000th?
Ten to the 10,000.
10 to the, yeah, it's going to be, here's probably a better way to think of it. It's 1 over 10 to the 10th, 1 over 10 to the 8th, and 1 over 10 to the 8th. And then we're going to raise this to a big number, which is going to be, say, 100, 10 to the 1 over 100. In other words, alpha is equal to minus, I'm sorry, alpha is equal to minus 1 over 100. Which number is going to come out as the biggest when we do this? Is this number going to come out as the biggest, this one or this one? Which one comes out to the biggest? We'll see if your arithmetic intuition kicks in here. It is going to be this number. It's going to be this number, which comes out to be, let's see.
Dr. Marks, did you want alpha to be negative 100 instead of negative 1 over 100?
Alpha is equal to, I did, you're right. That's right. That was on the outside. Shouldn't be a comma there. Shouldn't be a plus. It should be this. And so we have 1 over 10 to the 8th raised to the minus 100th power, right?
And Dr. Marks, did you still want the 10 to the 8th to be in the numerator?
Boy, you're right. I can't do this. Okay, here's the point. If you get a calculator out and you apply this stupid thing, maybe I should just go to a stupid spreadsheet. Maybe that's the way to do it. Okay. Let's do this. Let me open up another sheet and not relying on my calculator, but let's do 1 and let's do 1,000. And let's do 1,000 or 2,000, for example. Now we're going to choose alpha. Equal to what? We want to choose alpha to be a very large negative number. Oh, am I sharing my screen? I'm not sharing my screen, am I? Shoot, that doesn't help you very much.
Mr. Arm.
There we go. Okay, so alpha is equal to minus 100, right? So I'm going to take this number to the what? To the power that I had here. There's my little caret. There it is. And put little dollar signs before that. And I'm going to do the same thing for the other two. Whoa. I made it too big, didn't I? Let's do to the minus 10th. I didn't have to go all the way out there. And it's still the same. Maybe I'm making these too big.
Dr. Marks, is there a formatting option to show more decimal places in the C column?
Yeah, maybe I need to do that. That's not working either. Oh, you know what I have to do? I still have to take the sum of these. And I have to raise that to I have to, first of all, divide it by 3, right? Because it's over n. And then I have to raise this number to the, whoops. This number, correct? I believe I did that. Okay, so this is the final answer. This is the h of minus 10. Let's make it a little bit bigger. Let's make it to the minus 20, see if anything happens. Okay, what you're seeing here is that we are getting the 1.05, right? And if we make it even smaller, if we do it to the minus 30, we're going to get closer and closer to 1, right? This is 1.03. So what is happening? This number is approaching this number. In fact, let me change that number. Let's do a 1.2 here and see what happens. You can see it's about a 1.2 there now. Minus 40. So this is kind of the engineering proof This is kind of the engineering proof that the aggregation for minus infinity is the same as the minimum over here. So this 1.2 is about the same as this. Now, here's a problem that okay, so therefore it does turn out to be the minimum of those numbers. Correct? This number approaches this number. The smaller that I make alpha. I'm probably going to run out of the computational accuracy here pretty quick. But there we're at 1.21. Here we're at minus 99, 1.21 there also. So we have to go out really, really far. Now let me put these between 0 and 1, which is normally what we would do. So I'm going to put this at 0.01 and then 0.02. No, and then I don't know, 5. Now we'll see, hopefully, that this should go to the minimum. In other words, at this point, this is the minimum, and this is the minimum. This is the aggregation for minus 99. If it was minus infinity, this would be exactly 0.01. So it's the minimum. So therefore, the more that we mess around with this, and the greater that we make the alpha here, okay, there we're getting pretty close to the 0.01. So the point is that what I've shown, I've kind of done an engineer's proof of it. I'll put a little smiley sad face there because I couldn't do the arithmetic. What we're having is that h of minus infinity is equal to, well, I've written it up here, is equal to the minimum of these values. Okay. In a similar fashion, you can go through the same sort of manipulation, that h infinity is equal to the max. H sub minus 1 is equal to what? 1 over A1 plus 1 over A2 plus 1 over A sub n divided by n raised to what? Raised to the minus 1 power. This is a mean which is known as the harmonic mean. So we have the minimum, the maximum. Now we have the harmonic mean. That's the harmonic mean. We'll come back to h sub 0 because that's a really fascinating one. H sub 1 is equal to 1 over n times A1 all the way up to A sub n. And that is the regular mean or the average that we're used to. Then we have h sub 2, which is 1 over n times A1 squared plus all the way up to A sub n squared. And that is going to be raised to the minus 1/2 power. I'm sorry, to the 1/2 power. And this is the mean square error, right? Or it's the square root of the mean square error. So it's the root mean square error, if you've heard of that. So this is the RMS value. And so these are the fun ones: h minus infinity, h infinity, and h sub 1 and h sub 2. The interesting one is h sub 0. H sub 0 turns out to be a sub 1 times a sub 2 all the way up to a sub n to the 1 over nth power. This is something which is referred to as the harmonic mean. No, I'm sorry, the Oh, gosh.
Geometric.
Geometric, thank you. Geometric mean. Now, this is very interesting. You'll notice that H infinity is bigger than H minus infinity, right? And as we go up, the H's begin to increase. So the H's, H of say alpha plus epsilon, where epsilon is greater than 0, is going to be greater than or equal to H of alpha. In other words, as alpha increases, the aggregation increases. You'll notice also that the aggregation goes from minus infinity all the way up to H infinity, the min to the max. So in that case, you're going to have, if you plot this H for a given sequence, if you plot this for a given sequence, that given sequence is going to start out at the minimum, and then as alpha increases, it's going to go monotonically increasing until it hits the maximum. So if your sequence has a 0 and 1 in there, it's always going to start at 0 and it's going to always end up at 1. Okay. Instead of doing this, I think I'm going to have you derive the geometric mean. I'll give you a hint. It implies application of L'Hopital's rule. And once you get L'Hopital's rule down, you should be able to derive this as a very interesting special case of this generalized aggregation operator. Okay. So with that, I think I'd like to share my screen again and give you some homework for next time to discuss. Where are we at here? Yeah, there we are. We'll go back over here to this sheet, and I would like you to choose a few short sequence of numbers between 0 and 1, and I would include 0 and 1 in that sequence. I gave you an example. They don't have to be very long, like 0, 1/3, 2/3, and 1, or 0, 0, 1, 1. And then I'd like you to plot H alpha as a function of alpha on the same graph. Is that okay? So if we did that, let me ask you. Well, maybe this one isn't as well. Let me try this. H of 0, 0, 0, 1. If we were to look, for example, at both of these graphs, as alpha went between minus infinity to infinity, it would start at 0 and it would go asymptotically to 1, right? And in doing so, which one of these graphs do you think would be on top of the other one, or can we tell? Do you understand the question? What I'm saying is, if we were to take one of these plots, say for 0, 1/3, 2/3, and 1, we know that H sub alpha as a function of alpha at minus infinity is 0, right? We know that H of alpha at alpha is equal to infinity is equal to 1. And we know that it's a strictly increasing function. So we know this function is going to go like this, some way. Now you change this sequence, you're going to change this graph, right? As you change this sequence, you're going to change this graph. So my question is, what would happen if you had the plot now, instead of this sequence, a 0, 0, 0, 1 as your sequence? Do you think that this corresponding graph would be below or above this H of alpha?
Probably below, because there's more zeros.
There's more zeros, exactly. And this has to do with Yeah, with the axiom of concerning the monotonicity of H2. So yeah, I'd like you to do this for a few and just kind of convince yourself. I think this is a very interesting property, but it also says that the general aggregation operator in some way is kind of useless because what it says is that you should be able to choose any value. Okay, that's what I get for multitasking. You should be able to choose any value between the minimum and maximum, and you can come up with an alpha that gives you that as the aggregation, right? So you can see that the aggregation is very general, but maybe in some cases general enough to be useless. Okay. So let's go back and share the screen again. So the first one I'd like you to choose. Are you seeing my spreadsheet? Thumbs up. Okay. Choose a few short sequences of numbers. Plot h of alpha as a function of alpha, the same graph, and make some observations. See if what you get makes intuitive sense from the different sequences that you choose. Okay. And one will lie on top of the other one. This should be a very simple assignment, and we'll see what happens here. The other thing I'd like you to show is that the Jaeger intersection and union are associative. This is a generalization of the involutive properties of the Jaeger and Seguino complements. We have the Jaeger intersection and the union. Are they associative? Do they obey the associative property? Also on page 50 of Clear and Folger, there are a bunch of other fuzzy ands. I believe that I have it up here for our perusal. Yes, I do. We'll need to share my screen here. Come on, Adobe Acrobat. Okay, you don't see my screen there. I have to share a different screen. I have to show the Adobe Acrobat screen. There it is. Okay, this is on page, I think I said, what, 50? I give you the page number in the homework. But here, for example, is the Jaeger min and maximum. And there's these other ones too, the Schweitzer and Sklar, the Hammacher, the Frank, the Du Bois and Prad, and the Dombey. And we are looking at these as being parameterized. The extent of this parameters is given by this relationship. The range of the parameters on the right side, one is the fuzzy union and one is the fuzzy intersection. So that being well and good, what we would like to do is, going back to the homework, is I would like you to look at this and except for the Jaeger, you've done Jaeger already. That was kind of covered in the text. Do any satisfy the law of contradiction or the law of excluded middle? Remember we said that the min-max did not solve these. Are any of these a solution to that problem of satisfying the law of contradiction and excluded middle? I would also like to see if it obeys this property of, I don't know, what would that property be? Of idempotence, if you will. No, this isn't idempotence. This is if A is equal to A is, in other words, I'm asking this. Did I double that? Is that idempotence? Is that idempotence, guys?
Dr. Marks, I think if you take the intersection of A and then intersect that with A again, and you get the same thing, I think that would be idempotence.
Oh, okay. You're right. You're right. So it's the continuous. Okay. And then what about associativity and the idempotence? Now, here is the problem. The math on this is going to get very thick very quickly. So I don't want you all doing the same thing. So what I propose is to kind of spread the misery here a little bit. I'd like to spread the misery and let's assign, I want to do this at random. So Sam, why don't you take the first one? I'm looking at you in the order that I see on the right. Ming Kun, if you could take the Frank one, the second one. And Matthew, if you could take the Dubois and Prad. And Colin, you can take the Dombey one. And just look at the properties there. And Innocent, you're last on my screen here, so I'm going to let you choose whichever you want, except for the Jaeger. Okay.
Dr. Marks,
Yes.
you said for me to do the first one, and you told Min Kun to do the second one, which is the Frank. So do you want me to do the Schweitzer and Sklar or the Hammer?
Yeah, I was thinking of you with Schweitzer and Sklar, of
Okay,
Ming
Sklar,
Kun, Ming Kun being the Hammacher.
Okay, then I think you might have enough. I think you may have skipped one when you assigned.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. No, we have 6 in the class.
Oh, okay, never mind.
Yeah, we have 6 in the class, so I think we're okay. So does everybody have their assignment? And make sure you write it down if you have the short-term memory of a goldfish.
There's 6 equations or 6 items.
There's 6 items, but we've done the Jaeger already.
Oh, gotcha.
Okay, we've done the Jaeger already. We've beat that down. So
Well,
this,
Dr. Marks, we did the Jaeger complement, right?
well, but I think in the homework, I give you a special thing where I want everybody to look at the Jaeger intersection and union.
Okay, great. Oh, I see. Okay.
And then I would like to, and I'm going to add this, is also to do the proof of the H sub 0 as the geometric mean. Okay, that's going to require a little bit of hoopatow.
Hey, Dr. Marks,
Yeah.
I didn't get assigned one.
Oh, wait, you're Sam Hammacher, Frank, you're Du Bois and Prad. The second from the bottom.
I thought I was Du Bois and Prad.
Yeah, Dr. Marks, when
Okay.
you started assigning, I think you started at the second one.
I did. Okay. So let's try it again. Sam gets Schweitzer and Sklar. Ming Kun gets Hammacher. Matthew gets Frank. Trevor gets Du Bois and Prad. That might be Prade. Anybody know French? And Colin gets Dombey, and then Innocent can choose anything except for Jaeger. Are we good now? Okay, so write it down. Okay, so that's good. So that should conclude everything that we want to do about fuzzy. I've spent a little bit more time on fuzzy than I wanted to, but that's fine. Okay, any questions or anything else on this? Okay, good. You know, I was kind of toying with what to do next, and I think we'll deal with swarm intelligence, because I do want you to do a computer project on this. This is really, really interesting. Swarm intelligence is the use of swarming rules that are used extensively by, for example, social insects in order to do stuff. And what is very interesting and characteristic about it is that the swarming occurs in accordance to very, very simple rules. Say, for example, that I had I was in the kitchen, and I spilled a bunch of Skittles, and they just went all over the floor. And I had these little robots come out, say 20 different robots. And here was the rule that they followed. They would go around at random, and they would, until they bumped into a Skittle. Then they would pick up the Skittle. Then they would roam around until they bumped into another Skittle, and they would put the first Skittle down. So now they're empty-handed. They run around randomly till they run into the next Skittle. They pick it up. They run around until they come into contact with another Skittle, and they put it down. Do you get the very simple rule that they're following? What do you think happens in the long run?
It'll start to accumulate.
They stack up. That's exactly right. And this is an example of the algorithm that's used for termites in order to remove wood droppings, I don't know, but wood fragments, and clean up what they're doing. It's also used by ants in clearing the dead. If there's a bunch of dead ants, then the ants can come along and follow that very simple rule. Now, there's an interesting emergence which occurs here, which is the stacking of the dead ants. But you know what? If you look down at the agent level, they're pretty dumb. Bugs, at least at the level that I'm explaining them, are pretty dumb. They're pretty stupid. They follow very, very simple rules, but together they work in a fashion which gives a very nice emergence. Now, if we were live and the class was a little larger, I would give you the following example. Everybody would look at two people in the room, and you choose at random. I don't need to even know who you choose at random, but you choose somebody at random. And then your job is to, as you stand up and you begin to move around, is to always place yourself in the middle between these two people. You get the idea? It's a very, very simple rule. Very simple rule. What do you think happens?
You get into a big blob.
You do get into a big blob. Is that apparent to everybody? Usually it's not that apparent, but you accumulate into a big blob. Is there a case where you could accumulate into two big blobs, say at 1,000 people?
Yeah, if everybody picked only people in their blob.
That's right. If the populations were kind of bifurcated and people in one area only picked people from their area, and another one accumulated and put people at another area, and there was no crossover between the two, you would have two different blobs. Okay, that's interesting. Now I'm going to go to a website, and I'm going to supply you the link to that, but it's very simple to remember. It's my website, and it has, I think, some very interesting things. Uh-oh. I came up on an insecure website, and I don't want to do that. Okay, I'm going to share my screen, and this will just show you. These are little computer simulations. They're not astonishing, but this is neoswarm.com. And this contains some of the work that I've done in swarm intelligence. And let me tell you something about the swarm intelligence problem that I just gave you. This was proposed by a couple of researchers. And they said, this is really interesting because you can work it out intuitively, but you can't do the math. Nobody can really take that emergent property or the simple rule of placing yourself between the two people and come up with the fact that they emerge together. I was at lunch one time with Dr. Gravagna. You all know Dr. Gravagna, and Dr. Gravagna is just an incredible person in terms of control theory. And I explained it, and he said, "Oh, no, I bet you can do that." And so we worked together, and he came out with a formula that actually showed the different results that you could get by following those simple rules. And he found out that there were other solutions also just through the mathematics. But this is kind of the exception to the rule. So let me show you what happens here as we do this sort of project. Let's see, this is a little video. And you can see all of the agents. These are all swarms. They each have two people, and they're trying to place themselves between the two people. They initially spread out, and the intersection has been totally randomized. So everybody picked two different people at random. And as you can see, as Colin forecasted, they begin to accumulate into a single bulb here.
Dr. Marks,
yeah.
We're just seeing the neoswarm.com front page if you're sharing something else.
Oh, really? You're not seeing
Yeah.
this incredible video?
Well, there's a couple frames we're seeing, but I think they're just the top frames on the website.
Okay, well, let me try again. I don't know what happened. I thought that if I shared the,
I think maybe if it
The
opens a new
screen.
window, potentially it won't share it.
tell you what, I'm going to share my screen and just put the, can you see now a little blue field with a bunch of white dots? You don't. Ah, okay, don't know what to do. Oh, I have an idea. Ready? How about now? Okay, good. Okay, here we go again. These are 1,000 agents. It's 500 by 500 field. That's the playground. And there has to be a step size and some other things. And so what happens now is that each one has chosen 2 other agents, and the job is to place yourself between those 2 agents that you randomly chose. And so this is what I was hoping to show you, but it didn't come through. So you can see we put little trails there on the agents to kind of see where they came from. And those trails fade out with respect to time. And you can see indeed they begin to collect. And with this example, there were no disjoint groups. So it all converged to a single result here. And things are getting more and more crowded as the swarms begin to collect more and more in a more and more concentrated way. We'll skip ahead a little bit here. Oh, it's full screen. Unfortunately, we didn't save it with a really high resolution. And you can see eventually it just collapses to a dot. Now, this was an example that Dr. Gravagna named the peacemaker, because it's kind of like these agents here, P sub J and P sub K, they are enemies of each other, and you're coming in as a peacemaker to place yourself between them so they don't get in a fight. Is that okay? So a second very simple rule is something called the coward. What the coward does is that the green dot here is a bully, and the brown dot here is your protector, and you want to place yourself so that your protector is always between you and the bully. Does that make sense? So it's exactly the same problem as before. You pick out 2 people, and you assume one is the bully, one is your protector, and you always move so that the protector protects you from the bully. And so we have a bunch of people doing that now. And what do you think happens here?
Do they all get into
Yeah.
a line?
Do they all get into alignment? Okay. Maybe so. Any other thoughts?
They might just get out from each other
They
in all
do.
directions.
They do. So let's go down here and look at this. This starts so small, all 1,000 different agents are in a single position. So their movements here are little microscopic movements. Let me jump ahead a little bit so we can see it. And we begin to see now a little bit of separation as we do the coward and we explode. And it's almost like the other example run in reverse. It gets larger and larger and larger. And there it goes. It's going crazy now. It's like a wonderful simulation of the Big Bang or something like that. And in this program, these agents could go out to infinity. And, you know, that was okay. But they always existed. So you can see in the coward, there is an explosion that does happen. It's kind of fun to watch. Everything gets off the screen, and every once in a while you see another little guy come there. There's a guy coming through, and there's a guy coming through. And these things are so dispersed now. It's kind of like an entropy, I guess, in a way. Okay, so that is the coward. And then the third example is the follower. This one is very simple, and Colin's answer is applicable here, where you put yourself in front of somebody else and you just always follow that person. You're a groupie to that person. You follow that person wherever you go. And here you do get a conga line, as you might imagine. Let's take a look here. So every one of these agents has another agent that they followed. And I don't know what seems to be happening. Everybody's following everybody else. So this is a case where there's no heroes at all. Let me skip ahead a little bit here. What is interesting here is you can see some kind of paths which are kind of being carved out, right? These paths are being carved out. And something weird is happening, right? These paths are continually followed. It's almost like you're generating little roads in the wilderness in a way. Wow, we'll skip ahead quite a bit here. Before we skip ahead, I want you to notice that some of these are following little loops. So let's skip ahead a little bit and see what happens to those loops. Okay, those loops are getting smaller. And right here is a dead end. It looks like this guy is following himself, maybe. In other words, this one doesn't move. So it turns out to be a sink in the swarm kind of adaptation. And as time progressed, oh, and this is a little singleton here. It's a person that probably chose himself to follow and is just sitting there turning around circles, not doing anything.
Dr. Marks?
Yeah.
Could those dead ends be also two that are following each other in a really tight circle?
That's a good point. It could be that also. Yes, it could be two that are following themselves in a really tight circle, because as we see, if we advance here, and I'll advance this video a little bit, as we advance, look at what is happening. In one case, we have this little circle where all of these guys are just in an ellipse, and they're kind of in a, I don't know, a conga line or something. And then this last one, there is a sink here, an SINK, and all of these elements are just disappearing into the sink. So this is what happens. Now, what Dr. Gravagna discovered in this follower thing is there could be an example of, and this came out of the math, not through observation, but it could be that these things just lined up and went on forever, like comets in the sky, just ever moving, ever moving, ever moving. And here is one of the examples. There's just a few, but these few are kind of following each other. This is a modulo display. So as things disappear from the right, they reappear on the left. As they disappear on the bottom, they reappear at the top. So it's a modulo sort of sketch here. But you can see, interestingly, in this follower that you don't have stationarity here. Rather, what you have is a continuous line of agents just following themselves. And after a while, they're just whipping along at a constant velocity. So that's another interesting simulation. Now, where do we use swarms? Oh, this one is still boogieing away up here, right? Where do we use swarms? Swarms is a useful model for all sorts of things. Not only can we as engineers use swarm principles in the design of things, but we also see swarms not only in insects, but we see them in everyday biological entities. To be a swarm, you don't have to move. You are characterized by the fact that you do something very simple, and with that simple operation, you have an emergent property. Consider, for example, a set of cells in your lungs. I know there's a number of different types of cells in the lungs, but one of the types of cells. They're sitting there, and one cell doesn't know what another one is doing. It's just following a little simple operation. Yet there is an emergent property that the lungs are breathing and doing things. So there is an emergence which occurs here. I want to go back, and then there's other applications. We'll find out that we can use swarms in search algorithms, something called particle swarm. We can use swarms in increasing efficiency in businesses. And I'll give you an example of that later on, but I want to look at the termites now because we talked about the termites. This is a very crude example of termites clearing a field. Now, the solid boxes are the termites that are carrying a piece of wood, and the little circles are termites which are not carrying pieces of wood. So remember, you bump into one, you put it down. I'm sorry, no, that isn't the case. I misspoke. The triangles here are termites carrying wood. The little dots are termites not carrying the wood. And these little results are pieces of wood. So hopefully we'll see them stacked. This is very interesting. It goes on, and I'll skip some stuff. We don't get into a single stack. But I do know, since I've seen this before, that this island down here at the bottom, if you can see my cursor, eventually disappears. If that island disappears, there's no way that we're going to get wood put back in this island. There's no way we're going to get wood taken back into the island. So it just pops around, and eventually this stack of wood will go away at the bottom, and there will never be wood there again. The only way that wood would be there for the termite simulation is if there was a bridge built of wood to that point, and that has a very low chance of happening. I want you to see this island go away. It's like they say, I've seen there it went. Okay, so you're never going to get wood there again. So this is looking at it from a little bit a different perspective. It's not stacking wood. It's definitely clearing the wood. Okay, that's well and good. Here's even one which is more fascinating. This one is also with termites, except that the termites have a drift. They have a little bit of drift in one direction. They don't move randomly. Up here, the motion of the ants was by a random walk, by a Wiener process, if you will. Down here is we have the termites, and they're kind of moving to the right. There's a little bit of drift, which we put in there as opposed to a random walk. You can see one of the very interesting emergent properties is that the termites begin to build tunnels. And I don't know if you've ever ripped off the bark of a tree and watched the termite or seen the termites underneath the bark of a tree, but it kind of looks like this in a way. And notice this is also modular. As it goes through the top, it comes out the bottom, and it goes off the right, it comes into the left. And that's not bad, because if you're doing a tree, for example, the tree is circular, so it is modular. If you go off one end, you go to the other end. Now, what is interesting, I don't know, there's a bunch of interesting properties, and you always see this in the emergence. Number one is the little circles that are in here. Do you see the circles inside the red? The circles inside the red is where the wood is at. And you can see these circles these termites are stuck there. And what they're doing is they're putting down their piece of wood, and then they turn around and pick up a piece of wood, then they put it down, and then they pick it up again. Also, what's interesting is you see some of these trapped ants are freed by other ants as they bump into them. You can see them, the ants kind of working their way through the wood one at a time. And if they bump into another one, they trade their identities. The one they bump into is the one that continues on. So we see this emergent property of tunneling just by adding a little bit of direction onto what happens. Okay. So that's where we're going next. I'll show you some other operations, and then eventually, well, then we'll talk about some engineering applications of swarm intelligence, and then I'd like you to, at some point, write a simulation for a swarm intelligence, because the idea is you just choose very simple rules, and you see what those rules do in terms of the emergence. And sometimes it's just incredibly fascinating. And again, like the examples I gave you for the termite picking up, and also for the protector and bully sort of swarms, it's really not clear what the emergent property could be. Then later on in the course, when we get into search, especially evolutionary search, we'll show how you can evolve. We'll show you how you can evolve a swarm to do what you want to by imposing simple rules. So we'll actually do a search and an evolution of a swarm technology to get it to do more of what you want it to do. Okay, that's it. I think our time is over. Any questions at all?
I have a quick question about that the example where someone goes to the mean of two other people they've randomly selected. So in the case where like you can write like a system of or a system of PDEs or linearize it as a system of ODEs if that rule is linear. So do all like the interesting dynamics tend to show up when the rule is
many of the dynamics do show up, and you'll see on NeoSwarm that there is a reference to the mathematics that Dr. Gravagna put together to indeed show this. And so, yes, it was done with linear control theory. The analysis was. However, many of the swarm sort of things are not subject to such analysis. Not readily. I'm sure that maybe if you looked at it long enough and scratched your head long enough, you'd figure out something, but a lot of them aren't. So any other questions? Okay, if not, thank you very much. Be of good cheer.